Okay, cool. So since you have learned about vectors in last in lectures last week, so we will talk about so here we will give you a very a brief overview about vectors, vector space, and the Warsaw vector field, and the Warsaw various operations acting on those objects. So we have vectors, vector space, and the Warsaw vector field, and the Warsaw operations acting on those objects. By the way, feel free to stop me if you have questions or you get confused. We can stop and explain more to make it clear. Okay, so whenever people talk about vectors, for example, let's take 2 dimension as an example. Like people write a vector. Okay, so we have a x component and x hat and y component y hat. So here x y, just two bases of this space, and we know that vx and vy just the components of this vector in this basis, and they are just numbers, right? And x, y, it's themselves are also vectors. And of course, for the same vector, if we write this vector in different coordinates, the components will be different, right? So for example, in the 2 dimension, we can write in the Cartesian coordinate, like what we did here, right? This is Cartesian coordinate. Or we can write the within the polar coordinates. For example, ER, using the basis of ER, E theta. In this case, the vector can be written as like this. So generally speaking, a vector can be decomposed in any basis, right? So we can, generally speaking, we can write a vector in this kind of form, Vi, Ei, right? So for example, in for the Cartesian coordinate, so by the way, so here I can be equal to 1 or 2. So in this case, E1 equal to X, E2 equal to Y. So here, this is a basis, this is a component, right? And for this one, for the polar coordinate, E1 is ER and E2 is the E theta. And I mean, this sum just tells you V1, E1 plus V2, E2, right? And usually we just ignore this sum. So when we write a vector, we write like a Vi, Ei. This kind of notation is called Einstein convention or summation, whatever convention. So in physics, we usually use this notation. Whenever you say two indices, if they're the same, meaning that we sum it over. So the reason why kind of we ignore this sum is because when Einstein dealt with general relativity, there are many indices. Sometimes if you don't do this, you will get like mu, nu, rho, alpha, like I, j, k, a lot of indices. So it looks like kind of ugly. So we just drop this sum symbol and have this. Yeah. So this is for vectors. So vectors are one important property is the component of the vector. the components of a vector can be different or must be different, different in different coordinate or in different bases. So vector itself, like a vector V, vector itself is invariant. I mean, vector is a physical object. For example, vector velocity field, acceleration field, they are physical, but the coordinates are like different coordinates. Different people may use different coordinates. They are kind of artificial objects. We know that physics should invariant, like for different people, like we say the same physics, right? Meaning that V is invariant, but the component, Vx, Vy, Vr, V theta, they are different because they have different bases. For example, if you want to transform the basis from xy to theta and r, so there's a transformation. Your components must have a similar transformation and combine, okay, let's call it S, combine those two transformation together, you will get this vector V itself is invariant. So let's look at an example. For example, I have a vector, sorry, I have a two-dimensional system. I have a vector starting at point 1, 1, and the angle with this x-axis is 45 degree, and assume the length is square root of 2. Of course, we know that in the xy coordinate, we can write this vector as 1, 1, right? So decompose this vector V along the x direction, along the y direction, you will get 1 and 1, or x plus 1. However, if you decompose this vector in the polar coordinates, you will get, ER. There's no theta component because at this point, the coordinate looks like this. This is the ER, this is the E theta. So you can see this vector V is parallel to the ER and perpendicular to E theta, meaning that the component of E theta is 0 and square root of 2 yeah. So you can see so here's the component is 1, 1. Here's the component is square root of 2, 0. So they're different because this vector, we are decomposing the same vector in different bases. Is it clear? So the message I want to convey here is the components of a vector will change if you change your basis. Actually, there is a transformation. I didn't talk about here. I think at this point, you don't need to know. Yeah, but eventually, if you learn more advanced classes, you will know. And for tensors, that's just it's just a generalization of this kind of vectors. You can think of a vector as a rank 1 tensor.
So a tensor would be like in the third dimension or the fourth dimension?
Okay, so after I talk about vector space, then I'll very brief describe what is tensor.
Okay.
Yeah, thanks for asking. Yeah, eventually, okay, rank. Okay, I will talk about rank. So basically, rank is the number of index here. So here you can see you have only one index, meaning that the rank is 1. For tensor, generally speaking, so if I have a tensor V, then it's a Vij, Ei tensor product Ej, something like that. You have 2 index. Then
Oh,
it's
okay. Thank you. That makes sense.
Yeah. I mean, generally you see a tensor is looks like this, right? Vij or whatever rho ij, you have two index. And of course, you can have more and more indices, ij, k, l, whatever. And in that case, we generally write like vectors, tensors in using their components. But actually, when you say it's a vector, it's a tensor, you should always specify the basis. Otherwise, you don't know what it is. You can say the same vector can must be different in different bases. Right. In some sense, it looks like a matrix. Yeah. Okay, so what is a vector space? Vector space, I mean, when you cannot talk about vectors without talking about a vector space, right? So vector space is just a space, sorry, space where vectors live. Meaning that you can imagine a vector space is a set of vectors. So we call kind of this abstract space vector space. And each point in this space is a vector. For example, this point can be x, this point can be y, this point can be x plus 2y, this point can be like any, I don't know, ER, this point can be E theta, this point can be zero vector, this point can be any like alpha x plus beta y. So alpha and beta are real numbers or whatever, yeah, something like that. So if you add any two elements in this vector space, you will get another element in this vector space. And if you multiply a real number with a vector within this vector space, you will get another vector in that space. There are several rows need to satisfy by the elements. You can Google online like a vector space. I remember there should be like 8 equations should be satisfied. But basically, it's like it's a closed space on the addition and the multiplication of with real numbers, something like that. And the worst distribution rows. Yeah. So one important thing you need to know about vector space is the dimension. Dimension of a vector space, by the way, we generally denote a vector space as a capital V. For example, in previous example, there are two bases, meaning that the dimension of the vector space is 2. Because there are 2 degrees for freedom you can change, right? So this the dimension of the vector space is also equal to the number of bases. In principle, we can choose any 2 linear independent vectors as bases. For example, x and 2x plus 3y. Of course, we can use them as bases because for any vector in 2 dimensions, we can kind of express this vector using this basis, some coefficient alpha, some coefficient beta, right? It's like for 2-dimensional, like R2, then we can choose 2 vectors. Any point in that space can be expressed using this kind of a coordinate, like yeah, x and 2x plus 3y. But we usually use the so-called orthonormal basis. Right. So so-called orthonormal basis. So orthonormal means the basis is orthogonal to each other and the magnitude of the basis is 1. So for example, for the Cartesian coordinates, we know that x dot x equal to 1, and y dot y equal to 1, and x dot y equal to y dot x equal to 0. So this corresponding to the normal, meaning that the length is 1. Here, corresponding to orthogonal. They're orthogonal to each other.
So can we use this argument for the number 2 in the homework, where it's like we already found 3 not orthonormal, but like 3 normal.
Yeah. I
vectors?
mean, sure. Yeah, that's totally fine, I think.
Yeah.
Because
okay.
in that case, you have 3-dimensional. The vector space is 3-dimensional. Is a 3-dimension, and you already have like 2 linear independent vectors, 3 linear independent vectors. So there's no, yeah, you can use the argument from the dimensionality of this vector space. It's totally fine.
So the vector space would just be like in this case, since we're talking about like 2D vectors, the vector space would be the entire like R2, right?
Exactly. Yes. Exactly. Okay.
So like the span of the vectors is just the vector space.
Yeah.
Okay.
Okay. So about Einstein convention, yeah, that's just like when you learn like physics class, like classical mechanics and E&M, and also quantum mechanics, that you will need it. We use it everywhere. Like it's very common. I will use quite often. Like later on, at that point, I can explain more, I guess. I think also this Einstein convention is not required in this class, but it's good to know. And also it's quite convenient to prove the like vector equations using Einstein convention. Yeah, I can give one more example. Like when I talk about the cross product. Okay, so talk about orthonormal basis. So in the polar coordinates, similarly we have this, right? Sorry, it's 1 and theta e dot theta equal to 1 and er dot e theta equal to 0. This is also orthonormal. And with journey, okay, so here use Einstein convention, we can denote this orthonormal condition as like this. Ei dot ej equal to that ij. That ij is just a symbol equal to 1 if I equal to j. If I not equal to j, it's 0, right? So for example, if I equal to x and j equal to x, then ex dot ex equal to delta xx, which is 1. And similarly, if you set I equal to y, j equal to y dot y equal to delta yy, which is 1. And if you set the 1 is x, 1 is y, then you get ex dot ey equal to delta xy. They're different, so it's 0. So this is just a compact way to write the orthonormal condition. Okay, so what else I want to say? By the way, it has a name. This symbol has a name. It's called conical delta symbol. Conical delta. Yeah, it's good to know. Okay, so let's talk about. By the way, so for any question? Okay, so since we have vectors, so we have a vector space, and we have vectors in this space. there are two operations we can make. One is so-called dot product or inner product, whatever. So it's a binary operation. So the input is two elements, like two vectors. The output is a number. So you can think of this dot product as a map. It maps two vectors to a real number. So u dot v. So written in components is given by ux uy dot vx vy, which is ux vx plus uy vy. Or using Einstein convention, it's just ui vi. Right. Yeah. Of course, you can prove this like using like a, because we know u is ui ei dot v is vj ej, so it's ui vj ei dot ej. So assuming they're orthonormal, so it's delta ij. ui vj delta ij is just ui vi. The reason is because this guy is non-zero only when I and j are equal, meaning that we can just replace this j with I. So you see UIVI. So
I have a problem understanding Einstein notation. The first line, why did you write down UI and VJ instead of UI, VI?
Okay, that's a very good question. It's because the Einstein convention. Okay, so if I write UI, very good question. Thanks for asking. I I didn't realize that because I just get used to it. If I write like this, there will be four indices are the same. Then you don't know how to sum, like which, like should I sum it over them or sum it over them? Is you will get messed. So instead of using the same index I can use different index for different sum, like I, j, j here. So this kind of I index is called dummy index, meaning that you can replace this I with any other symbols, like k, it doesn't matter, because eventually you will sum them over. Does it make sense?
So what is dummy variable?
Dummy variable meaning that a variable that will eventually be summed, like a k. So like this, right? U1, ux, ex plus uy, ui. Right. Of course, you can also use I, ui, ei, which is ux, ex plus uy, ui. So you can see they're the same. It really doesn't matter which symbol you use. It really doesn't matter, because eventually you will sum them over. It's just like you are doing an integral, like a x squared dx. You can write it as a y squared dy, right? So eventually you will integrate it over. So the result is independent of which symbol you use. Similarly, eventually you will sum this index over. So it doesn't matter which, like you can use I or J, it doesn't matter.
Oh, okay. So what you're saying is the I and J in the dot product are dummy variable. Therefore, you can use any variable that you want, and you want to make it clarify it so that you use the I and J, the different symbol to represent.
Exactly. Yeah. Does it make sense? Okay, so so this is a dot product. So cross product. So cross product is more unique, is more exotic compared with dot product actually. Cross products, there's no cross product for like higher than 3 dimension. So if your dimension is higher than 3, there's no such thing. So when we talk about cross product, we usually say it's 3-dimensional vectors. Okay, so what I want to say about, so it's similarly, it's worth a binary operation. Give me the input is the input are 2 vectors, and the output is worth a vector, another vector. So it's I mean, you can also write this kind of cross product using the like index notation. Yes, just to explain to you, I think, let me write it down. Please let me know which step is unclear so we can clarify on that. Okay, so you can write this U as ui ei cross vj ej equal to ui vj ei cross ej. By the way, this cross product only kind of is a product between vectors. So this kind of a u and v are numbers, they're components, remember? So you can just factor them out and put them in front of this product. So the product only happens, essentially speaking, it only happens between this kind of bases, the vectors. So what's this? We know that E1 cross E2 equal to E3. Assume this is 1, E2, E3, something like that. So E2 times E3 equal to E1. So if you cycle those kind of index, you get all the 3, like E3 cross E1 equal to E2, right? And also E1 cross E1 equal to 0, E2 cross E2 equal to 0. Then there's a so-called Navier-Civita symbol IJK-EK. So this one, epsilon IJK equal to 1 when those 2, 3 indices are different and in this order. If IJK equal to 1, 2, 3, and you cycle them, you get a 2, 3, 1, 3, 1, 2. And you get a -1 if IJK, you permute this guy like even odd times, you get 1, 3, 2. You can say if you exchange those 2 index, you get 1, 3, 2. And you exchange these 2 index, 2, 1, 3. This is 3, 2, 1. You get -1. And otherwise, you get 0. Otherwise means at least 2 indices are the same. In this case, so EI cross EJ equal to epsilon IJK EK. This is just a compact way to write this all these kind of equations. For example, if I equal to 1, J equal to 1, so you get E1 cross E1 equal to epsilon 1, 1, K, EK. So we know that if there are 2 indices are the same, then it's 0. You get this equation. So if you I equal to 1, J equal to 2, E1 cross E2 equal to epsilon 1 to K, EK. We know that, of course, 1 to 1, E1, you can K can be 1, and also K can be 2, and K can be 3, but they are 0 because their 2 indices are the same. So only the last term survives, but we know that epsilon 1, 2, 3 is 1, so E3. So we get E1 cross E2 equal to E3, which is exactly the first equation. So this is just a compact way to write those equations. Is it clear?
Yeah, is that the Levi-Civita symbol?
Yeah. It's just a so-called Levi-Civita symbol. This, by the way, here I also use the Einstein convention. Here, those two indices k, meaning that I should really sum them over. You can see here, I sum them over, k equal to 1, k equal to 2, k equal to 3. Yeah.
So if two indices are the same, then we sum over that indices.
Uh-huh.
That's what you're.
Yeah. Okay, so okay, so from this notation, you can say the k component of this vector is actually u I v j epsilon I j k, right? Because this ek is the corresponding to the case basis, right? So the coefficient corresponding to the case component. So the case component of this cross product is this. And this result agrees with our Euro definition. Like we know that U cross V equals to how to calculate it. Ijk is Ux, Uy, Uz. Sorry, it's U. Vx, Vy, Vz. And like we know that U cross V, according to our previous, the K component equal to epsilon Kij, and Vj. By the way, here I put in previous equation I write Ijk, but I can put this K to the first place because I kind of cycle this index. It doesn't matter. So let's say if K equal to Z, the third component of this vector, according to what we have here, then is, okay, let's use this one. So Ij, Z, Ui, Vj. I know that this guy can be this guy is non-zero, only I, J, Z are different, meaning that I equal to X, J equal to Y, or I equal to Y, J equal to X, okay? Otherwise it's 0, according to the definition of the Levi-Civita symbol. So I is X, J is Y, I is X, so J is Y, plus I is Y, J is X, I is Y, J is X. So this guy is 1. This guy is -1. So you get this. And according to this definition, the third component of this vector is given by, which is exactly Ux Vy minus Uy Vx. You can see this guy is exactly this guy.
I had a quick question.
Yeah.
I just don't understand the purpose of what we're doing. Are we trying to learn how to compute the cross product?
Exactly.
Or...
So here, it's just another way to write the cross product.
So why is this any more elegant or simple than just doing the determinant of the matrix?
Okay, so that's a very good question. Okay, at this point you would say, okay, this is so complicated. There are so many indices. I'm so confused. That is also what I feel like when I first learned this stuff. Like I learned this stuff when I learned the classical mechanics. Like I really get confused. Like so many indices, and it's really confused me. But later on, when I learn more and more like physics, I felt like this is really an elegant way to express vectors and tensors. Okay, there are several advantages over this kind of vector notation. One is this like in the chat, It's a more compact way to express the equations. Of course, when you do vector cross product, like for example, if you want to verify this guy equal to something, okay, of course, this one is a dot c minus a dot b. It's quite difficult to use this kind of cross product to prove. Maybe you can prove it like in some way, but I can prove this equation using this kind of epsilon symbol like in 1 minute. Very easily we can do it. And also other like a cross b dot c cross d. This kind of equations, if you want to simplify them, you will find this kind of index notation is very convenient. Another, I think, is a more important reason is because this kind of index notation can be generalized to tensors. There's no way to use vectors to represent like tensor stuff. Essentially speaking, when you define tensors, you should use this kind of index notation to denote it. For example, if you math tensors in your previous class, you will see like this kind of ij, like the xy component, xx component, yy component. There's no way to put a vector sign like in front, like on top of it. It's always in component form. Yeah. But I think at this point you just need to know we can write this kind of vectors in using this kind of a component like index notation. I'm pretty sure if you are a physics major, eventually at some class you will need to use this kind of stuff.
Okay, thank you.
Yeah, sure. So this is what I want to say about the vectors and the vector space and also the operations. Any questions about this? Yeah, it's very good to ask me questions, and yeah, I think it's good. Otherwise, I don't know like which part is confusing, and yeah. Thanks for asking me questions. Okay, so if you guys have no question, I will continue with vector field. Okay, vectors is just a very basic elements. A vector field is our purpose, actually. It's our final goal. So what is a vector field? Vector field is like, for first, we need to have a space. For example, our real space, like this, we are in 3 dimensions, so it's a 3-dimensional space. And also we have a vector space. And there are many vectors in this, the infinite vectors in this vector space. Then we assign each point in the space. It's called P1, P2, P3. Assign each point in this real space with a vector. So at this point, we assign a vector here, V1. At this point, we assign another vector. They can be the same or can be different, it doesn't matter, generally speaking. So like a V3. Then at each point, there is a vector. Then we form a vector field. So we can write this guy using like a Vx, y, z. This is a map from R3 to the vector space, meaning that the input is a point, the output is a vector. So input, you tell me which point you want to look at, I will give you the vector at that point. And this point itself is in a 3-dimensional space where you can write x, y, z to a vector. So between space, the map between space and space, we use this kind of arrow. And between point, between elements and elements, we use this kind of arrow. This is just a mathematical notation. If you open a math book, you will see this kind of notation. So is it clear what is a vector field? Okay, so for tensor field, similarly, at every point you assign that point with a tensor, that is a tensor field. And the scalar field, you can regard a scalar as a rank 0 tensor, right? So scalar field is like you assign each point with a scalar. Scalar is a kind of like just a number. There's no component, 0 component. That is why we call it rank 0 tensor. Okay, so what else I want to say about vector field? So vector field, another way to understand the vector field is like for each point, you think of, you can copy this vector space, like at each point, there is a vector field. They're the same. So each point on this, this is a vector space. This at each point on in this vector space is a vector v1, for example. So this is a v2, whatever, p1, p2. So it's like for each point you choose a vector. Of course, you can choose another vector, for example, p1, p2. This is a vector space. You choose another u1, u2. Then you get another vector field. So this is a vector field of v, x, y, z. And this is a vector field u, x, y, z. Of course, you can do the inner product, like the dot product, dot with u, x, y, z. You will get a scalar field. A quantity that is a scalar. It's also a field. Of course, you can also, if your vector is a 3-dimensional vector, then you can do cross product. Then you will get another vector field. Okay, so in this case, the space is R3, is like the real space we live in. The space here is flat. Okay, so I'm not sure I want to talk about it. Okay, let's forget about this. So what I want to say is, what if this guy is curved? Then it's curved, it's more tricky. If you want to compare the vectors at different points, you cannot compare them directly. You need to transport this vector from this point to another, to this point P2, and then compare this. After transport this guy with this guy, you cannot compare this V1 and V2 directly. But let's forget about it because we don't need it at this point. Our space is flat. And okay, so this is about a vector field. So what operation we can make? There are 3 operations basically. One is a gradient. It acting on a scalar field. It will give us a vector field. And also divergence. It acting on a vector field. It will give us a scalar field. And also curl. It acting on a vector field, it will give us a vector field. So those are three operations acting on a vector on a field in general speaking. So if they are not field, they are just a vector, then this kind of operation acting on that vector is 0, right? Because there's no XYZ dependence, meaning that when you take a derivative, it's just a number. When you take a derivative, you always get 0. So only when you have a vector field, you can talk about differential stuff like integration, because there's a space, there's a domain, you can do integral, you can do derivatives. Right. By the way, the vector space, like the vector we talked about before, you can think of the space is 0 dimension. It's a point, meaning that at that point it's just a vector. There's no XYZ dependence. It's just a constant vector. So when you take a derivative, or you will get 0. When you have some space to move, you can do this kind of operation. And also, all these 3 operations have physical meanings. They are not just mathematical objects. So for example, for the gradient, so a gradient of a scalar. For example, if this scalar is the energy potential, this minus gradient of this energy potential will give us the force. Force is a vector. Energy potential is a scalar. For example, a very well-known example, like it's a one-dimensional example. In 1D, we know that the potential of the spring potential is given by 1/2 kx squared, right? This is actually a scalar field in 1 dimension. You can see at each point in R in this R1, you have a number associated with that point. And you take a you take a gradient. In 1 dimension, this gradient becomes a derivative. So this is nothing but minus kx, the spring force. And in like generally speaking, 3 dimension, it will give you the force. If a force can be written in this form, then this force is called the conservative force. This is like one of the homework problem, meaning that for this force, you can write energy potential associated with that force. And
I had a question about that example that you just did. I was just wondering, like, why do we use the negative? Like, I understand, like, that's in the equation, but I'm still, like, a little bit...
Oh, okay. So I think that's just a convention. Or, I mean, you can...
Like directional convention?
Absorb this minus sign into this phi. Then this phi becomes minus x squared. But actually, I think maybe we want the energy to be positive. So we just put this negative sign in front of this.
Okay, I see. So because the force is going in like the opposite direction or something.
Yeah.
It's going inward. Okay.
Yeah, exactly. Yeah. It's like you have a potential, then the force should be kind of pointing to the place where have lower potential, right?
Yeah. Okay. Yeah.
So there's a negative sign. It's quite intuitive. Okay. So I think time goes quite fast, and yeah, we're already run out of time. So yeah, it's good. I think gradient and divergence curl. Next time we can talk about this and more stuff. If yeah, that's it. So any question?
So I have something to ask you about the discussion worksheet. You wrote down the answers, but I have a hard time mathematically understanding it.
Oh, you mean like the discussion worksheet?
Yeah.
Oh, that is written by another TA, I think.
Okay.
Yeah, but if you have question, you can ask me. I can work the answer this.
In Einstein notation, what's the difference between superscript and subscript? Because
Okay,
I can see many of them.
Okay, that's a very good question. Okay, I can stay here. If you have no question, you're free to go. If you have question, you can stay here and we can discuss more. So what is the difference between the upper index and lower index?
Yes, that's correct.
So in our case, in 3D, in our case, there's no difference. The reason is quite simple. You know, so whenever we talk about product, right? The reason need to back to this kind of inner product. So when we talk about dot product or inner product, the rigorous definition is UI VI, or it's like this. Yeah, it should be written like this, meaning that there's a matrix. To talk about the inner product of a vector space, you should always specify the metric of that vector space, meaning that when you have the metric, you can measure the distance, you can measure the angle between different vectors. And in 3 dimension, in our case, the metric is 1, 1, 1. So meaning that this metric tensor, this metric Jij is delta Ij. So it's Ui Vi delta Ij, which is Ui Vi. Remember what I said? When you have a delta Ij, you can always replace. Sorry, this is J. You can replace this J with I. So in this case, you can
why
say.
does the
Sorry, yeah. You can say to make a lower index vector, you should start with an upper index vector. You should always combine this vector with the metric of that vector space. In general speaking, this guy is not equal to Vj. However, sorry, Vi. So this is a vector. This vector in general is not speaking. In general speaking, they are not equal. Sorry. However, because you are talking about a flat space, meaning that the inner product, like the metric is 1, 1, 1, which is delta Ij. It really doesn't matter. You get a Vi. And it matters when your metric is not 1, 1, 1. For example, in the special relativity, you have a fourth dimension corresponding to the time, which is -1, 1, 1, 1. In this case, upper index and lower index are different. For example, if you have a vector, like for example, I have a vector mu V0, V1, V2, V3. Then you write down what is mu. This guy is -0, V1, V1, V2, V3, meaning that V0 equals -V0. They are different. In this case, they are different. This is because V mu equal to G mu nu or V nu. So you set mu equal to 0, you get G 0. By the way, 0 meaning sorry, this is 0, this is 1, this is 2, this is 3. 0, 1, 2, 3. We usually call the t dimension, like the time dimension, as like 0. So 0, mu, v, mu. And this is also Einstein summation, Einstein convention. So because this guy is diagonal, -1, 1, 1, 1. So this guy can be non-zero only when v equal to 0, which is v0. G00 is -1, -0. So we get this lower index equal to minus upper index. Because in our case, it always 1, 1, 1, 1. So when you go from the upper index to lower index, so for example, my v1 equal to g1 v1, which is g1. We know that 1, 1, 1 is diagonal, so this guy can be non-zero only when v equal to 1, so 1. But we know that g11 is 1, so 1 times v1. So they're the same. So if your metric is 1, 1, 1, then it really doesn't matter which where you put your index.
Oh, thank you.
Yeah, is it clear? Like
so I just repeat what I understand. For the subscript, it represents the matrix. Matrix of the space that you talked about so far.
Yeah, like this. Yeah, so this metric.
And for the upper subscript, it looks like some kind of element of the space. Yeah.
Yeah, and actually there's a name for this kind of okay, so okay, let me stop recording first.